All right, let's dive into one of the most fascinating and, honestly, kind of weird ideas in all of calculus, infinite series. We're going to explore the beautiful, mind-bending math of what happens when you just keep adding numbers forever.
So right off the bat, here's the central question. It feels like a paradox, doesn't it? I mean, if you just keep adding and adding and adding, shouldn't the sum just blow up to infinity? Well, the crazy answer is, sometimes it doesn't. And figuring out that sometimes is the key to this whole thing.
So here's our roadmap. First, we'll lay out the puzzle itself. Then, we'll open up the mathematical toolbox we need to solve it. After that, we'll talk strategy, uncover a really surprising application using polynomials, and finally, we'll figure out how we can measure just how precise we're being. It's going to be a wild ride.
Okay, first things first. Before we can solve the puzzle, we have to understand the playing field. What are we actually dealing with when we talk about adding numbers forever and ever?
An infinite series is pretty much exactly what it sounds like. You take a sequence of numbers, like a half, then a quarter, then an eighth, and so on, and you just start adding them up, and you never stop. The huge question is always, where is this sum actually headed?
And that question leads to two, and only two possible outcomes. The first is that the sum actually settles down, getting closer and closer to a specific finite number. We call that convergence. The other option? It just grows and grows without any limit, shooting off towards infinity. That's divergence. Our entire job, really, is to figure out which of these two paths a series is going to take.
So how in the world do we figure that out? It's not like we can actually sit there and add up an infinite number of things. Of course not. Luckily for us, mathematicians have built an entire toolbox of really powerful tests that can tell us a series' ultimate fate. And here it is, the master toolbox. Now, I know that looks like a lot. It can be pretty intimidating, but don't worry. The real secret here is that different tests, like the ratio test or the integral test, are custom built for certain types of series. You don't need to be an expert on all of them. You just need to know that for any given job, there's a right tool waiting for you.
In fact, if you're studying for something like the AP Calculus exam, the sources show that you can really cut through the noise. A few key tests just keep showing up. If you can master these four, the nth term, geometric, p-series, and alternating series tests, you're going to be in really, really good shape.
Having a garage full of tools is one thing, but being a master mechanic is about knowing exactly which wrench to grab and when. The same is true here. Having a strategy isn't just helpful, it's absolutely crucial if you want to tackle these things efficiently.
The source material really lays out a great strategy that works kind of like a flowchart. First question always, do the terms themselves shrink to zero? If they don't, boom, the nth term test tells you it diverges. You're done. If they do go to zero, then you check for special recognizable patterns, like a geometric or p-series. No luck? Look for clues. If you see factorials, you should be thinking ratio test. If you see the signs flipping back and forth plus, minus, that's a huge hint to try the alternating series test. This kind of step-by-step thinking saves so much time.
Okay, so we can figure out if an infinite sum adds up to a single number. Cool. But so what? Why does any of this actually matter? Well, this is where it all gets really incredible. This isn't just some abstract math puzzle. It's actually the key to building and understanding some of the most important functions in all of science and engineering.
And here it is, the big payoff. It turns out that we can use these infinite series, which are really just infinitely long polynomials, to perfectly represent functions that seem way more complicated. I'm talking about things like sine, cosine, or e to the x.
The magic recipe for doing this is called a Taylor series. It's this brilliant procedure that uses a function's derivatives, all calculated at one single point, to construct an infinite polynomial that acts exactly like the original function. And if that special point you pick is zero, we give it a special name, a Maclaurin series. Check this out. This makes it so clear. On the left, you've got the good old cosine function from trigonometry. And on the right, that's its Maclaurin series, just a simple, never-ending polynomial. And here's the part that should blow your mind. For any value of x you plug in, those two things are exactly equal. We've just turned complicated trigonometry into basic arithmetic. Now, some of these series are so important, the sources say they're basically worth memorizing. The series for e to the x, sine of x, and cosine of x are the big three. Being able to spot these in the wild is like a mathematical superpower.
So we can use an infinite polynomial to stand in for a function. That's amazing. But, in the real world, we can't actually add up an infinite number of terms. We have to stop somewhere, and that raises a really important practical question.
Right. If we chop off our infinite series after, say, the first 10 terms to get an answer, how close is that answer to the real thing? How much error did we just introduce? Is our approximation pretty good, or is it way off? We need some kind of quality control.
And guess what? We have it. It's called an error bound. Think of it like a guarantee. It's a number that tells you the absolute maximum amount your approximation could possibly be wrong by. We have specific tools to calculate it, like the alternating series remainder or the Lagrange error bound, so we can be totally confident in our answer. Just look at this number. This comes straight from an example in the source material. By using just a few terms from a series, we can guarantee that our approximation is off by, at most, 2/10,000ths. That's an incredibly tiny amount of error. It gives us an amazing level of precision.
And that's really the big takeaway here. The power of infinite series isn't just that they let us approximate these really complicated functions. It's that they let us do it with a known, controllable, and often ridiculously small margin of error. This is exactly how your calculator figures out the sine of some weird angle. So I want to leave you with this final, kind of mind-bending thought. If these beautiful, elegant functions like sine and cosine could be completely broken down and rebuilt from nothing more than simple addition and multiplication, just repeated forever, what does that say about the fundamental fabric of mathematics itself? It kind of suggests there's this deep, hidden simplicity that connects everything. It's a pretty cool thing to think about.